Hello, this is my classical mechanics project around center of mass. I used this weight, 3 toothpicks, and then just a paracord and this multi-tool. So pretty much what I ended up doing, as you can see, is using the paracord, tied it around that hammer, and then set it on a toothpick. And I had to weigh it down with that weight in the back, as you can see, just to keep it in place while I tried to organize everything first. So the goal here is to keep that entire system of the 3 toothpicks, the paracord, and the hammer suspended only by that top toothpick. And so to do that, you set one perpendicularly to the paracord as a crossbar, and then what you do with that third toothpick is you set it so that it's pretty much jammed in between that crossbar and your top toothpick. Now, as you will see, this was kind of hard to do in a timely manner. It took me several attempts, but I'll eventually get it working. All right, and this is looking like all right, and it looks like I ended up getting it to work. With that staying in there on its own, I felt good enough to take off of the weight, holding the system down. And as you can see, it is now entirely on its own, standing. And I'll pick it up at my camera here and show you a better look at the system. And there it is, freely suspended. My visual explanation of basically how this ended up working. So on the left, the bottom or crossbar toothpick, I denoted it as toothpick 3, is denoted by the blue arrow. And then in both images, that diagonal toothpick is denoted with cyan, and I addressed that one as toothpick 2. And then in the right image, shown with green, that is our top toothpick or toothpick 1. So the way this ended up working was that with the weight pulling down, that being our little multi-tool, the energy is being stored in our middle toothpick through the tension in this paracord. Then through that, it's starting to cause the middle toothpick to push up against the top. And that's going to be equal to the tension. So with that, we now know that if the center of mass is where it ended up being, of borderline towards the origin in terms of x and y, and very far below in terms of z, we know that it's just directly counterposed to the vertical component of the force pushing up against our top toothpick from our second toothpick, or the middle one. And then through that, we have to know that they cancel. So that little toothpick in the middle is what's holding up this entire system. It's providing the force needed to prevent the top toothpick from falling off, or, with the same result, the bottom weight pulling the entire system down. So just to reiterate everything I said, just to make it clear, the middle toothpick is placed in a way that causes it to have an equal and opposing force to the tension caused by the weight, and they cancel out beneath the top toothpick. All right, and here's the math I did for the project. So what I ended up doing was solving for the force on the first or top toothpick given by the second or middle toothpick to hold the system in suspension like this. So I found the length of a toothpick being 5 centimeters. And then what I ended up doing is, knowing that's the diagonal, I formed a 3, 4, 5 triangle using the geometric identity and used that to get my angle, which ended up being 53.13 degrees. Now, with this, I ended up using those to get their place in the system, given that I defined my origin as 0, 0, 0, as shown in my drawing towards the upper left of it. That is our origin. And with toothpick 1, we have an x of 3 and 0 everywhere else. And then I also showed the mass of a toothpick to be 100 e to the negative 3 grams. Toothpick 2, I said, was 3 in the x, 0 in the y, and 4 in the z. And toothpick 3 being 0, 0, and 4 in the z. And then I also included our hanging mass in this system, and that was 0, 0, and 24.13 centimeters, with its mass being 312 grams. And I got that from Googling the product. It was a just specific kind of multi-tool, as you saw. So then I used all of these values to begin calculating the center of masses for each coordinate. And the first being x, I of course set it up so that just multiplying the mass times where it is in terms of the origin. And for x, I ended up getting a very small value of 0.00192 centimeters, or 0.00192 e negative 2 meters. For y, there was nothing shifting in the y, so I knew that it would be on the origin there. And for z, I knew we would include 2 of our toothpicks, the bottom and the middle, or toothpick 3 and toothpick 2, and our hanging mass. And all of that calculated out to be our z being 24.06 centimeters, or 24.06 e negative 2 meters, in which we finally had our center of mass being 0.00192 e negative 2 meters, 0, and 24.06 e negative 2 meters. With that found, we could then move on to the next step of finding that force. And really, what we knew now is that since the center of mass was so close to the origin in terms of x and y, we could reason that the tension will be applied directly downward, perfectly opposing the vertical component of our second toothpick's force. Since there isn't any vertical motion, these forces must be equal and opposite, so they cancel each other out. Given that, we knew that it was the vertical component of our toothpick 2 force, so I wrote it out accordingly. Then I equated it to our tension, which was the pulling down, which was also equal to our gravitational force of just mg. And then throwing that all in, I ended up getting 3.061 newtons. And just dividing that sign over, I ended up with 3.83 newtons. That's that force that was pushed upwards by the second toothpick onto the first.